Grant, Nadiri, and Sunny, you guys can start once you see fit. Thank you.
Okay, so good afternoon, everyone. Today we'll be sharing our project on voxel-based morphometry analysis of SMRI data in healthy individuals. So before we introduce our current project, we wanted to briefly explain why our research direction changed from our project pitch. So our initial topic focused on ADHD medication history, where we plan to examine whether medication moderated age-related brain structure differences using both VBM and SBM. However, after considering the feasibility and feedback received, we realized that the topic required two complex analysis pipelines and had a relatively narrow methodological gap, making it less suitable for our project timeline. Therefore, we refined our topic to focus on neuroresilience in healthy adults exposed to ACEs, and this allowed us to use one clear SMRI method, which is VBN, while addressing a more clinically meaningful research question. So these are the things we'll be covering today. Starting with the background, ACEs refer to stressful or traumatic experiences during childhood, such as abuse, neglect, and household dysfunction. So previous research has shown that ACEs are linked to poorer mental and physical health outcomes. ACE exposure is also associated with increased risk of later psychopathology, including depression, anxiety, and trauma-related symptoms. However, this relationship is not deterministic. Not everyone who experienced childhood adversity develops psychiatric difficulties. Some individuals remain psychologically healthy despite ACE exposure, suggesting that there may be resilience-related mechanisms that buffer against the long-term effects of early adversity. So from a neuroimaging perspective, ACE exposure has been associated with changes in brain structure and function, especially in systems involved in stress and emotion regulation. So key regions commonly discussed in literature include the hippocampus, amygdala, anterior cingulate cortex, prefrontal cortex, insula, and reward-related circuitry. So these areas are important because they are involved in functions such as stress responsivity, emotional processing, cognitive control, and reward processing. Previous studies also linked higher ACE exposure to reduced gray matter volume in limbic and frontal brain regions. So this provides a rationale for examining gray matter differences in our sample. However, one limitation in the existing literature is that many ACE and trauma neuroimaging studies focus on vulnerability to psychopathology, while less is known about the neural basis of resilience. So in this project, we define resilience broadly as maintaining healthy functioning despite exposure to adversity. Neuroimaging studies suggest that resilience may also be associated with regions such as the amygdala, ACC, hippocampus, and prefrontal cortex. However, the neurocorrelates of resilience remain limited compared to the neurocorrelates of vulnerability. So our study addresses this gap by investigating whether ACE-related structural brain differences are present in psychiatrically healthy adults. So the aim of our study is to examine whether ACEs are associated with whole brain grain volume differences in psychiatrically screened healthy adults. So using SMRI data from the NIMH healthy volunteer dataset, we applied a VBM to access gray matter volume across the whole brain. So our research question is ACE score associated with whole brain gray matter volume in psychiatrically screened healthy adults? And based on previous literature, we hypothesized that higher ACE scores would be associated with voxel-wise variation in gray matter volume. So by using a healthy sample, we reduce the influence of current psychiatric disorders. So I'll now pass the time to Grant to share more about our methodology.
Thank you, Sun Yi. So as she shared earlier, we will be pulling out data from the NIMH Research Volunteer Dataset, as there was strict screening in place in order to ensure that all participants are psychologically and physically healthy. So as she also shared earlier, we'll be looking at ACE scores as the IV, as well as controlling for various other factors that we believe will be relevant. This will be shared later on. Next, please. So the first step of our data process was actually cleaning the data, as our data set included multiple phases of data collection, through which the initial team actually had changes throughout the methodology. So for this, we actually ensured that we cleaned everything by hand in order to ensure that all our data included SMRI scans as well as scores for ACEs, PHQ-9, which we used as a proxy for evaluating depressive symptoms, and GAD, which we used to evaluate anxiety. So to ensure that there were no relationships between ACEs as well as the psychological outcomes, we performed initial regression analysis on R to ensure that all participants. Sorry, Sunyi, your mic. To ensure that all participants were psychologically healthy. So we also noticed that our data was not pre-processed. So the next step for our methodology was to actually pre-process this on MATLAB using SPM12. So we followed standard processes including segmentation, normalization, modulation, and smoothing to ensure that our final data was ready for VBM analysis. Next, please. So this ended up with us having one Excel sheet as well as our participant data in CSV form as well as our scans, which were all included in our repository on GitHub. Throughout our cleaning process, we ended up with 82 viable participants for analysis and used A scores as our IV as well as the total gray matter volume within the brain as our DV. We controlled for other variables such as individual variance in the total intracranial volume as well as participants' age and sex. Next, please. As can be seen on our GitHub, we actually faced our project entries steps in Python. So the first of which was loading all of our participant and scan data, followed by a mass univariate GLM fitting before we moved on to using statistical analysis, particularly FDR correction, to find out that unfortunately there were no significant differences across participants based on A scores. With this, I'll hand over to Nandini in order for her to explain how all of this can be contextualized.
Moving into the discussion, while the null findings initially seemed to contradict past literature, like Lim's meta-analysis, which strongly linked childhood trauma to volume reductions in frontal limbic regions, but we believe this lack of structural divergence actually points towards a phenomenon known as structural preservation. This is the brain's physical capacity to preserve its structural integrity and resist atrophy even under severe life stress. Because our sample came from NIMH healthy volunteers dataset, anyone with a history of psychiatric disorders was excluded. Therefore, our high ACE cohort represents a uniquely resilient subpopulation. But what drives this structural preservation? We propose three main mechanisms. Next slide. First, top-down buffering. Resilient individuals tend to show stronger active prefrontal cortex, where regions like medial PFC and ACC successfully downregulate hyperreactivity in the amygdala, shielding it from chronic stress. Secondly, lifestyle buffers. Behavior plays a massive role. For instance, recent work by one of the researchers in 2026 shows that regular physical activity, 150 to 300 minutes a week, directly strengthens functional communication between ACC and amygdala, acting as a biological shield. Thirdly, resilience operates as a complex adaptive system. It isn't just one factor, it's a dynamic combination of internal genetic protection paired with strong external environmental assets like robust social support. Moving on to the limitations of our project, our size was relatively constrained, and we used FDR correlation, which lacks spatial specificity. Furthermore, our sample is highly homogeneous and psychiatrically healthy, meaning we lack a vulnerable comparison group. Lastly, our E-scores rely on retrospective self-reports, which introduce potential recall bias. To address these, future research should shift from a broad whole brain sweep to a targeted ROI approach, focusing strictly on stress-sensitive areas like hippocampus or amygdala. We also recommend using Cat12 pipelines for a more precise tissue segmentation, explicitly modeling lifestyle covariates, exercise and sleep, and integrating rested state MRI to capture dynamic functional connectivity, even when structures look identical. In conclusion, our study demonstrates that a high burden of adverse childhood experiences does not guarantee gray matter loss in adulthood. When individuals remain free from psychiatric illness, their underlying frontal limbic structures show remarkable preservation. Ultimately, neurobiological vulnerability is not a fixed outcome, and psychological resilience is clearly marked by physical maintenance of a healthy brain. Thank you.
We open up questions to the floor. I have one question. Do you all have the data, the results of the NIMH paper or publication themselves?
If I'm not wrong, it's just open source data. So like they did not have any analysis. The only thing that they published was the how they collected the data and how they recommend the data would be used. They didn't do any analysis on their end.
Okay, so like it's difficult for you to say like since you didn't show any ACE related effects, whether this replicates their data or not.
Yeah.
Okay. Are there any other ways you think that you could compare with anything in their database to make sure or validate something that, like we are not doing things completely wrong from what they intended?
Okay, well, we did find one study which was also released this year, which had something similar, but they did adopt an ROI approach instead. They did find specific areas, but I think that our study differed in two main ways. The one which was we looked at total gray matter volume instead of ROI, or regional. I think they did regional gray matter instead. And then the second being that we had a much smaller sample size.
So it's a different data. It's a different data set.
Yeah, it's a different data set as well.
Okay.
Yeah.
Well, that might be one step, like just to make sure if there is a published work, even if it's a different data set, maybe replicate some of their methods as well. Just a sanity check. Not saying that this is a good presentation. I'm just suggesting for future work. Yeah.
We have time for one more question.
Hi. So I just wonder, while analyzing the association between brain structure and the ACE score, are you do you just do the linear regression, or you are building a contrast? Yeah, that's my questions.
If I'm not wrong, we skew a bit more towards linear regression as opposed to contrasting high versus low. So we put it on a scale of like 0 to I think 5. That was the highest within our data set for the A scores. Yeah.
Okay. Yeah, because I look into the repository you uploaded. So I think a lot of the score are 0. I mean, a lot of participants don't report any issue about their personal experience on that aspect. So maybe I think we could do contrast, or try to using like 0 versus not 0 or something else. Yeah, because to me it's a new variable. I never heard about it, but it looks very interesting. Yeah, try to identify people with or without a certain experience. So maybe it's not just a nominal scale factors. It's more like categorical factors to my understanding. Yeah. Okay, that's just my questions. Thank you.
Okay, thank you very much. Should I pass on to the next person? Jessica, can you share your slides? Perfect.
Okay, can you hear me?
Yes, we could. Yep.
All right, thank you. Hi everyone, so I'm Jessica from NTU Taiwan. My research question is, can transformer generated emotion labels complement the human annotations in naturalistics, films, fMRI, and where? Oh, sorry. Okay. So here I got a problem. The research gap, the effective fMRI is gated by its annotations layer, and that layer is human derived. So in my emo films data sets, we have so the data set paper, they have 44 annotators, 50 items, and 1 Hertz every film. That is, I think that's just slow and expensive to produce. So which is why I think automatic label is attractive, but cost isn't the text. So the validity is, and the question is whether an automatic label recovers the human signal, not whether it turns or it returns a number. So I'm keeping that open. And so I have the pipeline, 1 human target and 3 methods arms, birds, and a stronger model, Gemini, and brain decoding. And so for the emo film data set, it is an open source data set on the Open Neural. And I collected 12 of the 14 films through our wireless outside the text meta scope. And the target is the human consensus for Pleasance order, the highest reliability valence item average across radar. So as you can see, the 0.58 reference is the pairwise inter-radar agreement, different yardstick from the consensus the models are scored against. And the consensus is denoised and easier to predict. So that's asymmetry matters later that I'm gonna show you. And here I have the pipeline. First, I collected the dialogue, the transcript, by using Whisper software, and then I run the sentiment posterior at 1 Hz, correlated against the consensus, and with the 2 seconds offset applied throughout. And we move on to the first arm. So I use 3 birds family models, 12 fins. So the result is the kind of pattern, not a row. So you can see in the figure 1 positive tear of steel. This is the theme tears of steel. Like around like 0.35 replicating across bird, the steel bird, and seabird, and the other 11 near 0. So the spaceman, the red one, the red line. So the spaceman looks negative, but that's a transcription artifact that I'm gonna show you next slide. On inference, I report no significance deliberately. The annotations are correlated over 80 to 110 seconds. So a bootstrap run on 18 to 54% false positive rate, which the result is anti-conservative and informative. So the evidence is the effect side plus replications across the models and film. And I did it carries through all the themes. So here, in one live fiber, just per segment sentiments recovers human balance only on 1 theme, not the other 11. And here, during running the data, I encounter a problem, that transcription contamination. And I think the 1 corrections can change the result. Whisper transcribe the diegetic songs, recited verse from poem, and sound text, and the model scored them as a dialogue. So 5 of the 12 themes contain this contamination. And Spaceman's, the Spaceman themes is the diagnostic theme that I did. Apparent are of negative 0.29, which I could have reported as real. So I removed the 94 seconds of songs and credits, and the negatives result collapses across on 3 models. And that concordance identified as an upstream artifact, not a model human effect. So my lesson learned here is diagnose the contamination before interpreting any correlation. And move on to the second arm, the Gemini 3.5 flash on the same isolated input as birds, 1 segment at a time. And the context is the next slide. So the figure is the per theme difference. So Gemini minus bird, each theme is all score is all control. And the shift is positive on 10 of 12 themes, and it pulls birds spurious negative towards 0. And the evidence is that shift across themes. So for an absolute level, I quote only the clean theme tears of steel about 0.47 below 0.58 reference. And the contaminated themes still show the difference. Seeing both model read the same transcript, but I attach no absolute rating. So, well, this is just preliminary and decrypted effect size. And here, so this one, I put Gemini into context experiment. So the manipulations changes only the input, a plus or -3 segment window. So on the dialog fields, agreements rises monotonically and per segment bird to isolate LLM to context LLM. So on the dialog light, after the range, as you can see, is essentially flat, a principal null. So context cannot supply a fact that isn't in the text. And tiers of still reaches 0.59 under the context, and the 0.58 line is a pairwise iterator. This is the noisier yardstick. So this is a consensus level agreement on the stream. It's not beating the humans at all. So this is within the Gemini isolations versus context SAM model, but I didn't run the context on BERT yet. So I back note context-based BERT versus Gemini claim. And I also asked myself, like, isn't just smoothing? So I got the answer. The signal does get mildly smoother, but the gain survives, drawing the most change time points. So this is the preliminary of the 4 themes. Yeah, fighting of the 4 themes. And the third arm, human valence decodes from one subject, occipital, both at about 0.21, leave one block out across validation, stable across regularization, occipital, so a valence correlated visual signal is not an effect per se. So I think this is just a proof of concept for my research, and the fair human versus automatic comparison, as you can see, is underpowered. So I only have like 7 share volumes, so I claim nothing from it. And the result is the convergence through independent arms hitting the same dialog density limit. And as Professor Josh suggested, so I think I will do a power multi-subject comparison is the continuation. Okay, so to summarize, now I have 4 stages, 1 structure, and the sequencing is my contribution of this research. And human consensus is the target, and per segment sentiments is the transcription limited and largely fail. And the LLM with added context partially recovers segment of 4 themes, but only where the dialogue carries the effect. And the neural data converge on the same boundary. So each stage is like the foundations to the next. And here, so in conclusion, so the transformer's text sentiment is not a valid, surrogate for human emotions annotation in naturalistic theme. And a negative result, here established with the conditions for when automatic labels do track human nouns characterized. And all right, limitations of this research, plainly, the brand arm is a single subject proof of concept, and the context experiment is 4 themes, and significant isn't recoverable on the single short themes. And the round trip validates the pipeline, not the radar generation, generalization. And the next I'm gonna do in the future work is a power multi-subject decode on a dialogue dense theme. And the context work is extended beyond 4 themes, including BERT, effective ROI decoding to separate effect from the visual signal. And yeah, okay. So I think that's all for my presentation. Thank you so much, everyone.
Thank you, Jessica. We should move on to the question section. I think Josh has a question. Yep.
Yeah. So great work. And I'm just wondering, for the decoding for the fMRI part, could you tell us a bit more about what you use to decode what? Is it possible to have like just 2 sentences and quickly say like what was the input used to decode what output?
Okay, so on one person's brain data, so I use the subject S07. I think so I use let me remember. I use the human annotation, the human annotations, the valence from one subject, and then that human emotions balance can be read out weakly from the visual area, because here I would say the proper text versus brain comparison had to limit data to trust. So as for now, the point is that the methods and the methods breakdown is the same kind of theme, the ones that without much dialogue. So I just use that in summary. So human balance decoded from the brain. I take the human's presence, other consensus, and see how well it can be predicted from the occipital bow signal. So here it's just only the human, no model involved at all, and it's a human rating versus the brain. Yeah.
So the bow signal you mean would be like from the occipital regions. So let's say it has a few thousand voxels, right?
Yeah.
Then every voxel has a value of a bow signal, and you just use those numbers to classify basically what valence is in the human output. Is that right?
Yeah. But actually, that is the most unfamiliar part.
Sure.
So I'm still figuring out. I just text with one subject, but there's a lot of things I still need to learn. So yeah, but your questions make me like read things and go it deeper.
No, I absolutely appreciate the difficulty here, and there's obviously quite a lot of different things you have to watch out for in bow data. It's not so simple, like it's just a bunch of numbers that you can use. There's quite a lot of biological background assumptions still, but we can take that offline on Discord. Since you have the project post, we can continue discussion there. Yeah.
Okay, thank you.
Great.
Thank you. So I think we don't have time for another question. We'll move on to the next person. Chilin. May you share your screen and put it up? Yep.
Hello. Can you see the? Yeah. Okay. So my name is Jill, and this is my project. I'm going to do a FNIRS brain behavior analysis on children with and without dyslexia. So dyslexia is a neurodevelopmental. Sorry. Yeah, I'm here. Yeah. Is it okay? Okay, thank you. Dyslexia is a neurodevelopmental disorder, but its neural manifestations vary significantly across different languages. And this is important because it leads to poor academic performance and even worse mental well-being. So previous studies have been trying to investigating the core mechanism behind dyslexia. And so far they proposed two functions, which are PA and MA. So basically PA is the ability to use the basic unit of sound or phoneme, and MA is the ability to use the basic unit of meaning or morpheme. And in alphabetical languages like English, phonological awareness is often considered the core factor. But the importance of PA or MA is actually depends on the nature of the language itself. For example, like Chinese, it is a logographic language. And previous studies suggest that morphological awareness actually are more important in reading development. So previous studies focus more on alphabetic languages and rely on behavioral measures. So this would be interesting to see whether Chinese-speaking children with dyslexia use different neural pathways during morphological processing. So these are my two research questions. The first one is to see which brain regions show different activation between two groups of typical and children with dyslexia. And also I want to see whether the neural activation patterns are associated with behavioral performance on literacy. So initially I focus on three channels, which are channels 6, 16, and 21. And these are selected for two reasons. First is that they show group differences in previous pre-processing. And second, these are also shown in previous studies to have specific relationship with dyslexia. So for example, channel 6 and 21 correspond to DIFG, and channel 16 correspond to MTG. So these are all brain areas that are related to reading. And finally, previous studies have reported correlations between neural activation during morphological processing and later reading outcomes. So this may be meaningful to examine the brain behavior correlations. So this project, we recruited 60 children, half with and half without dyslexia. And we use t-test to make sure they are age matched. So they have to perform a morphological awareness task with 32 channels. So this is like FNIRS. They have it's kind of like a map to use light to detect the oxygen change. And they also have to perform 9 literacy behavioral performance. So it's a word of mouth, so you can see here Chinese character recognition, word reading, and so on. So basically, these are machine like do with machine, and these are paper and pencil tests. So they are independent tests. And this is an example for what we do in the experiment. For example, for this morphological construction test, they have to answer like if a chain for hands is called a hand chain, what would a chain for a foot be called? And they should answer like foot chain or 脚链. And for the FNIRS task, they have to choose the meaning-related words. For example, if the Q is 鸡腿, and they have to answer, they have to select between chicken, egg, and machine, and they should select this one, chicken, egg, because it's meaning-related. And machine is a distractor because it has the same sound with the target, but a totally different character. So the preprocessing is as follows. The first raw FNIRS were sampled at around 4 Hertz during the MA task. And also here, I want to clarify something 2 weeks ago. I remember someone asked about the timing, and I said 5 seconds, but I think I misunderstood the question. The 5 seconds is the noise cropping. So we discard the first and last second to avoid noise. And the frequency is actually 3.9 during the MA task. And then we did a first level GLM on MATLAB. So we found that the significant channels are as follows, 6, 16, and 21. And these are all like the pre-processing in MATLAB. And what I want to do in this project is to see the HBO beta estimates to do correlation analysis. So initially, I want to see whether there are brain behavior correlations on these 3 channels, and to use Python to test this. Yeah, so I know it's a bit complicated, so I try to visualize with it. So basically, there are 2 tests, and these 2 are completed before the project, and here I want to see the correlation between these 2. Okay, so first one is data visualization. This is like, it's interesting and easier to look at, because before this, all I see is a bunch of numbers, but now with this, I can just, this is just a screenshot, but with this, I can see each data clearly once I move the mouse on it, and even perhaps identify some patterns. And initially, I calculated Pearson correlations between brain activation and behavioral measures using Python code. So 2 weeks ago, I examined only 2 behavioral measures, and none of them are significant. So initially, after discussing it with TAs, I think there may be a selection bias. So I use an exploratory whole brain analysis, again using Python to compute and make a heat map. And just like make a scatter plot. Yeah, but again, there is no significant results. There's not even like some pattern in it. So as I said 2 weeks ago, I try to see whether there are more correlation between other behavioral measures. Yeah, because we have 9 behavioral measures in total, so there will be 3 times 9, which are 27 values here. But again, only one is significant here. Yeah, so the possible reason may be that reading difficulties may involve different distributed network level differences rather than problem in single channel. So also, brain behavior relationship may be complex and nonlinear. Finally, previous studies also suggest dyslexia involves different coordination across reading-related networks, such as rapid number naming or processing or sound processing. And so initially, I first tried to turn this into a heat map because, there were 27 values. It's a little bit hard to understand it. So now I turn it into a heat map to visualize, and it's shown here that only channel 16 shows stronger brain behavior association with picture vocabulary. And but I try to look back and think what I want to what I want to do in the first place. I want to see whether dyslexic and typically developing children use different neural pathways. So I think instead of using grouping them all together, I should separate them and inspect them separately. So then I do a heat map again seeing try to see correlation patterns between them. And here's something I think is more interesting. So on the left side is the children with dyslexia, and they show positive correlation. And this may indicate a compensatory recruitment because they need more, perhaps they need more cognitive resources to process reading. And especially, yeah, you can see here again the channel 16 and the picture vocabulary naming. As for the TD, there is a correlation. Okay, so yeah, so I can see here that channel 16 show the strongest brain behavior correlation. And from this project, I learned about Python-based visualization and writing correlation code. And in the future, I may increase the sample size and investigate about the channel 16 and what are there about RAN and vocabulary measures. Yeah, thank you.
Thank you. Pass on to question time.
Thanks, Ling, is it? Difficult task to do with your apneas. I think one of the things that may help you from the beginning is to decide on the circuitry for reading that you want to look at. So usually we have the dorsal ventral, the dual root theory for reading, and then to map onto that with your channels. So you could have more focal. So you have the dorsal more for phonological, the ventral more for your morphological processing. Then you can map on your channels accordingly.
Yes.
Your channel 16 is more IFG, right?
Yes.
Yeah, that's
MTG. 16, I think, is MTG.
MTG. Okay. Yeah. Which, I mean, it's good that you get some significant findings over there, though it's tough with the heat map and all that. But you may want to think about how that would then help you to be more focused. So you have a priori kind of analysis, and then you could show more of how your dorsal, because usually dorsal, you didn't get anything at the parietal, right?
No. Right.
Yeah. So then to sort of hone in on that. Yeah.
Okay. Thank you very much. Yes, I will do it.
We have time for a question and more a little bit. If not, we'll pass on to the next person. Thank you, Chi-Ling. Due to outage issues at Chelsea's, we'll move on to the next person on the list first. So it'll be Isaac. Isaac Teo.
Yep. Hi.
Oh yeah. Hi. Just for your screen, we can hear you clear, loud and clear.
Is my screen sharing?
Yes.
Thank you. Then I'll just begin. Good afternoon, profs and fellow classmates. So today I'll be presenting my some results on my study on cluster analysis and machine learning prediction of brain age and its associated phenotypes in autism. So autism basically is characterized by social communication impairment and restricted interest or repetitive behaviors. And one way that ASD is being researched on is through using cluster analysis to cluster different profiles of ASD. For instance, high-low functioning or in terms of their severity of symptoms. And in this current study, I'm using the MRI data to generate a brain age prediction and to calculate a brain age gap. So essentially using the MRI data to predict their brain age and minus away their chronological age, this will give the brain age gap estimation, which is useful to assess neurological conditions such as ASD. And ESD particularly assesses advanced versus delayed brain development. So currently there are some discrepancies in findings in terms of whether advanced brain development is associated with greater ASD severity or lower severity. And one of these reasons could be due to the way that we classify brain age. So one study simply z-scored it, and anybody with a positive brain age is classified as having advanced development, and then negative brain age with having delayed development. Another study added in another bracket in between, whereby if you're within negative 0.2 and 0.2 z-score range, then you're classified as having balanced development. So in this current study, I'll be using brain age prediction, and then use cluster analysis with brain age and the phenotypes to identify whether or not adding brain age into cluster analysis helps to profile ASD differently. And in doing so, we should be seeing that there's more than one stable cluster being formed, and this would indicate that there are distinct brain age cognitive symptom profiles among ASD individuals. Subsequently, I also use the MRI data to predict whether or not to predict which cluster it belongs to. And so from here, we should be seeing that able to do this above chance, which would indicate that there are certain brain profiles that are associated with these cluster subtypes. So to train the brain age model, first I'll use the Abide data set. There are 299 cognitively normal controls. Using the MRI data and their chronological age, I train a ridge regression model, and then after that test the model. From there, I got the testing parameter results. So preliminarily, these were the results, and quite clear-cut, there were two outliers. In examining the structural connectivity z-scores, we see that these two outliers have values that are 19 or 18 standard deviations above the mean. So after removing them, then this is the final model, which gives mean absolute error of about 1.72 and RMSE of 2.16, and the correlation between the predicted age and the individual's actual age is about 0.74. So this is more or less within range of other studies in the literature, which has about a 0.7 to a 0.9 range of correlation value. So with this brain age model, I would then train to predict the brain age of the ESD individuals. But before that as well, I would also have to correct for age bias. Essentially, you can see on the left graph that as an individual, as chronological age increases, there is a decreasing brain age delta trend. So to correct for the brain age, I pass the linear regression through it, and for every individual, we then correct this brain age correspondingly with this linear regression. Okay, then thereafter, with this model, I apply it to the ESD population using the MRI data, put it through the trained model, and I'll generate the predicted age. And from there, I calculate the brain age difference for each individual. So getting the predicted values on the left graph, and then in the center, we're calculating the brain age delta. And then finally, after correcting for the brain age bias, after correcting for age bias, then that gives the brain age delta corrected values for each individual. So finally, then I'll put it through the cluster analysis model. So for the cluster analysis, I'm using the ADOS scores, cognition scores, and the brain age data, passing it through a hierarchical clustering model, and from there, derive different clusters with different characteristics. So for the first analysis, I did it without the brain age data. And then later on, we'll do it with the brain age data to see whether there are differences in the results. So in using hierarchical clustering without the brain age data, you see that there are two main clusters. Based on the silhouette scores, two clusters are optimal. And so in cluster 1, we see that, in cluster 0, which is the group on the left, we see that there's a group of ASD individuals with lower ADOS scores, whereas in cluster 1 on the right, there's a group of individuals with higher ADOS scores. So in this clustering process, the brain age delta wasn't used, but it is just represented here to, I wanted to see whether there are differences in across the groups in terms of the brain age delta. But in terms of the statistically significant portion, yeah, only the ADOS scores were significantly different between both clusters. So after that, I did a cluster analysis with brain age data and based on the silhouette scores, whereby higher the silhouette scores, the more optimal, the more recommended the number of clusters is. So the optimal number of clusters would be 3 clusters in this case. And you can see that across all 3 clusters, there are differences in terms of the IQ, ADOS scores, and also brain age delta scores. In performing pairwise comparisons between the 3 clusters, we see that there are significant differences across more or less all variables, except for ADOS social and ADOS communication, whereby between cluster 1 and cluster 2, there are no significant differences in ADOS social and ADOS communication. So essentially, aside from these 2 black boxes, ADOS social and ADOS communication between cluster 1 and cluster 2, we see pairwise differences between among every cluster. So from here, I was thinking like, it means like if an individual has a low brain age delta, chances are he probably will be correlated with low ADOS scores based on like cluster 0. But in performing correlation between the brain age data and the various variables, we see that there's no significant correlation after correcting for multiple comparisons. So this could mean that while brain age might be useful as a general snapshot of the brain and might be useful for clustering in terms of forming different subtypes, it might not be so applicable in the fine details of observing correlations with the IQ or ADOS subscores. At the same time, it might also mean that in these different clusters, brain age might be accounting for unique variance that is not accounted for by IQ or ADOS subscores, and might be applicable in this sense. So finally, I used the MRI data and using a cluster subgroup, passed it through an elastic net logistic regression model, and from there get the testing parameters. So I did it for structural and then for fMRI differently. For structural MRI, basically these are the variables that I have, and train an elastic net logistic regression model using nested cross-validation method. And from there, see that I'm not able to do it just slightly above chance. So because there are 3 clusters, and so the balance accuracy will be 33.3% if we're able to do this at chance level. So it's currently at 0.382, which means that using structural data, it does not really predict which cluster you belong to very well. So from here, I thought that, so from here we see that we have 3 clusters, and I was thinking like, okay, what if with MRI data I'm able to identify correlations with the different clusters, and these correlations differ across groups. So what I did first was I did a correlation between each structural connectivity with the phenotypes, and see that in cluster 0, there's a significant correlation between these 2 variables with the stereo behavior ADOS scores. And in terms of cluster 2, we have a range of variables that are correlated with the ADOS social subscale. But in terms of the rest of the variables and structural connectivity, there weren't other correlations. So from here, I used these significant results and did a Fisher Z transformation, and I wanted to identify whether there are differences in correlations between the different clusters. And these are the significant findings. So if, for example, we look at the second line, it's saying that the association between the ADOS social scores with the bilateral lateral orbitofrontal gray volume, this correlation in cluster 1 is about -0.297, but in cluster 2 it is 0.537. And so there's a difference in correlation, which might suggest that across different clusters, there are different correlations. So thereafter, the same thing for fMRI, and subsequently I'm looking at doing.
Hi, sorry, Isaac. Time's run out. Can you just give us a very quick 2 or 3 lines and summary, please? Thank you.
So I think beyond clustering just by IQ and ADOS, adding brain age inside the stratification also helps, and it supports that we have 3 distinct neurodevelopmental trajectories. And across the 3 clusters, we see that there are differences observed in the associations of ADOS social scores with structural connectivity. Yeah, thank you.
You have time for one question.
I have a question about your clustering method.
Yeah.
Yeah, you used hierarchical clustering from SciPy.
Yes.
And based on my understanding, it doesn't produce like an X number of clusters. It produces like a tree or something like that, like a dendrogram.
Yeah.
So I am curious how you defined like cluster 0, cluster 1, cluster 3, something like that.
So the dendrogram essentially, I might be wrong on this part. It gives like the distance between how well the clusters group together. And so
yes,
so from the dendrograms, the silhouette value suggests which number of clusters is optimal. In that, the higher the silhouette value, it means that there are more like the clusters group together better as compared to the data points group together better in this number of clusters as compared to when we have other clusters.
Okay, and what was your linkage matrix? How do you define the distance? And you have to feed like a linkage matrix into the clustering function. So what was your distance? Well, it's okay. Like, is your repository in the Discord channel?
Not yet.
I remember to post it, and we can just go over that. I can look at your code later. I'm just curious. Yeah, thank you for the clarification.
Thank you for the question.
Okay, thank you very much, Isaac, for presentation. Moving on to next group is Jia Hao and Zi Yu. Yep. Yes, please.
Okay, hello everyone. Today I will going to present our project Brain Connected during the also fear anticipant and the loneliness reduction after the mediation training. And the first, we are the Jenna Zhou and the Jia Hao Guo from the GAI-BMS from the National Taiwan University. Both of us are the team of the Dr. Zheng Zhong. And this is Jenna speaking for this speech, the presentation. And before we beginning, do you feel lonely? And previous research suggests the loneliness may be the relative the lower empathies. So in the simpler term word, when the people feel lonely, they may report they feel less connected to other emotionally. And the score word is probably the perfect example here. Very lonely and no very empathies and clear not interested in the social bonding, just like the boring adult. But behind this struggle, there is a serious scientific question. If the loneliness is associated with lower empathies, can we reduce the loneliness and improve the social connect? So one possible way to reduce the loneliness is the meditation. So we found the paper focused on the meditation training can reduce the loneliness and increase the empathies. It's also the use of fMRI data and whether the loneliness is related to the neural response during the empathy relative text. And they include the 108 participants in the study and assigned them to early the loving kindness meditation called the LKM, or the Programming Muscle Relaxation PMR, for the 4 weeks intervention. And after the 4 weeks of the training, participants will compact the surface and underwent the fMRI scheme. And during the fMRI test, the participant will experience the two types of the situation. The first, they will directly experience the painful and non-painful situation. And the second, they observe that another person receive the painful and non-painful simulation. And they decide will allow a research to compare direct pain experiment and observe the pain fear anticipant. The key idea is they observe another person's pain can activate the empathy rather the brain system. And this study will conclude the LKM empathies. Also, they use the not the stronger evidence that the loneliness change the best neural empathy response. So maybe the story is not finished. They create a new question for our project. Could the meditation affect the social connectivity function and enhance the empathy, thoughts, loneliness reduction? The knowledge gap is their priority work mainly focused on the regional activity or pattern the simulation. And here the knowledge gap is the prior work mainly focused on region activity and pattern simulation. So let's know about the text-based functional connectivity during the observed fear anticipant. So our aim is to examine whether the loneliness reduction after the mediation training is associated with the connectivity between the affect empathy region and the methodized region. And our hypothesis is the participant with a greater loneliness reduction will show stronger connectivity between the inter-issuer and the regions such as the TPJ and the MPFC. So the associate may be the stronger in the loving kindness mediation group than the relaxing group. So we use the open neural database. And from the original study, the database is increased fMRI data from the mediation training participant, as well as the behavior questionnaire data. And the data already organized the BIDS complex structure, so which is useful for reported neural and image analysis. And here is out of the concept model. Start with the intervention, LKM or the PMR training. The intervention may reduce the loneliness, then loneliness will reduce maybe relative change in the affective empathy network, such as the inter-issuer and the DACC. This region may link the interaction with the metalysis or social connecting network, include the TPJ, MPFC, or STS and PCC. And here, the network level will change may relative to subject empathies or social connecting. So here our GPPI has 3 main steps. We first build the GLM contact other fear vs the safety, other pain and no pain, other specified fear, and other specific pain condition. And we then select the inter-issuer and the TPJ and the MPFC as the C regions. By combining the physiological signal from these regions, will physiology text condition will generate the GPPI interaction terms and analyze. It seems the condition dependent change in the functional connectivity across the brain. So our results. And here is the first level, decide the measures. They include the experiment condition together, and we corresponding the post-event regressor and motion parameter and the nothing regressor we also include to reduce the nose and the hand motion effect. And the next is the figure present the average standard block time series for the 5 regions. The signal will show the similar temporal pattern across the different brain regions, indicate stable signal throughout the experiment. And the next is heat map to show out the We observe that the rule is the specified connection and each color is represent the test contracts. And the color indicate the Spearman correlation coefficients, where warm colors represent the positive correlation and the cold colors represent negative correlations. And we see the strong negative in the right insula and to the MPFC. They during the other specify the fear condition. And we take a look at the positive associations and suggest the participant will greatly the reduction in the loneliness tend to the show strong the test-dependent connectivity between the right AI and the MPFC during the other specific fear anticipants condition. And because the result is based on the 10 participants, so they could be considered as poor and require the confirmation in the full data set. And we also see the individual in the LOK and the PMR. And the origin bars represent the reduction in the loneliness from pre to post intervention, while the blue bars represent the right and insula to the MPFC GPP effect during the other specific anticipant condition. And here is so interesting. We can see about the PNR group show the much greater the valuability than the LOKM group. So here our preliminary data result not really support our hypothesis. Also, the medication was associated with reduce the loneliness. We did not observe clear evidence to include in social connect function. And thanks.
Okay, thanks for the presentation. How many people were in this group for now? 10, is it?
Yes.
So far, are there more in the data?
Yes, they total have the 54.
Oh, so okay, so you're just trying out on the first few.
Yeah, we want to see which the brain areas connected.
Okay, all right. I noticed one funny thing is you had that bar plot and then the bars are above the 0 line. This is just a visual. Yeah.
Yes.
Is this just an artifact or is there what's happening here?
I think maybe they have two groups. So in the LOKM group, they maybe have more like a mediation effect inside.
No, but then you see the green bar are above the 0 line. It's not touching. You know what I mean? Or is it just on the projector screen? I don't know if my eyes are playing tricks.
Yeah.
You see what I mean? Like the green bar is not exactly on the 0 line.
Yeah.
Is there something wrong with the plotting function?
Yeah.
Well, you want to check that. Just make sure that you don't have any bugs in your thing.
Cool.
That maybe at first it looks like it's just a visualization thing, but maybe it's something fundamental, and then I don't know.
Yeah.
Okay. Anyway, yeah. Thanks.
Okay, so if we don't have any further questions, we'll pass on to the next person, Cindy Caroline. Yeah.
Okay, can you all see my screen?
Yes, we can see and we can hear you loud and clear.
Okay, thanks. Okay, so hi everyone, I'm Xin Ru from Department of Psychology at NTU Taiwan. So my final project topic is EEG signal analysis and classifications of multisensory stimuli using machine learning. So this is the outline for my presentation today, started from the introductions. I'm using an EEG dataset, and the research goal is to investigate whether EEG patterns corresponding to different and to evaluate patterns in EEG data to develop reliable predictions. And for personally, I hope to have developed hands-on experience in EEG signal preprocessing and machine learning development. Okay, this is a dataset descriptions. I'm using the Open Neuro dataset, which is the EEG semantic imaginations and perception dataset. So this dataset consists of the EEG signals of imaginations and perceptions across 3 different modalities, which is image, text, and auditory. So the test in this dataset is there will be 10 blocks of tests, which in each blocks will have 5 trials in each of the modalities. So there will be 15 trials for 1 blocks, and in total there will be 150 trials for each participant. Okay, so this is the data analysis workflow. I divided into 3 parts, which is the first one is EEG data preprocessing. The second one is stimulus event analysis, and the last one is machine learning classifications. And I'm doing all of this in Python in Jupyter Notebook. Okay. For the EEG data preprocessing, the step is divided like this, which is the first one is import the data, set montage, batch channels, detections, referencing, filtering, and the last one is ICA. And for the stimulus event analysis, it includes event extractions, epoch segmentations, and ERP analysis. The last one is machine learning classifications, which include feature selections, machine learning classification, and also the evaluations. So starting from the EEG data preprocessing, the first step is to import and read the data. So they actually have
sorry Cindy, just sorry to cut you off.
Yeah.
Are you using a wired mic?
Yes.
Yeah, maybe avoid brushing it against some sort of surface. We are hearing popcorn seasoning noises.
Oh,
and
I see.
we can't hear your voice very
Okay.
clearly. So yeah.
Okay. Is it okay now?
Yeah, you may proceed. Yep.
Okay, so for the EEG data preprocessing, the first step is to import and read the data. So they actually have 13 participants in total, but I'm just using one of the subject from the dataset to run for the preprocessing and to build the machine learning models. So I'm using the subject 10 session 1 data, and it including 128 channels and also 4,000 more seconds of time range in the dataset. I actually run for this dataset for so many times. The first time I use it, preload equals to true, but then I found out it crashed my Jupyter Notebook kernels lots of times, so I just changed it to false. So the one that I uploaded to the GitHub is actually preload equals to false. Okay, and also I defined the EOG channels in the first time when I import the data. Okay, so this is the PSD plot for the data set. We can see that there's actually a lot of spikes in 50 hertz and also 100 hertz, which is the power line that need to be filtered out in the next step. Okay, and also the second one is to set the montage, because in the data set that they provide, they don't really give the files giving the locations of the channels of each of the channels in the data set EEG. But so I'm just using the standard 1005 to set the locations. Okay, and the next one is the bad channels detections. For the manual bad channels detections, there are actually no bad channels was defined in the dataset. So I run for the automatic bad channels by using PyPrep and crop the data set to timeline from 400 to 1,000 seconds. And these are the bad channels that I get. So because in the first step, I set the preload equals to false. So for the next step, like referencing and interpolate bad channels, filtering and also I want to run the data set successfully because don't really know
Sorry, Cindy, your mic's causing issues again. Could you try to hold the mic like hovering above? Maybe it's rubbing against your clothes while you're talking, and we can't hear you clearly. Or put it closer to your mouth or something. Thank you.
Okay. Okay, I'm just going to continue. Okay, because I set the preload equals to false in the first hand. So for the next step, like referencing, the interpolate bad channels, filtering, and also the ICA will run successfully in the Jupyter Notebook because I don't really load the data in the Jupyter Notebook. So for the next step, I'm just going to use the code and the way that they use in the original data set. So they actually provide the preprocessed data. Yep. So for the next one is filtering. They use notch filtering and also height pass filter to filter the data set, which notch filtering is to remove the power line noise, and the height pass filter is to remove the yeah. And the last one is the artifact detections. They want to separate the artifacts into 50 channels, into 50 sources, and also use the method of FASTI. Using the images components and apply the ICA, they finally get the clean data set, which is also the data set that I used to build the
you have
machine learning
to,
model.
I don't know if there's a way to change the mic thing, because it it just keeps having some sort of static thing. Is it because it's on battery? Is it using battery? Yeah. Is it using batteries?
No.
No, it's part of the computer, is it?
Yes.
Is it part of the
Maybe I
computer?
tried to change it. Yes.
Huh? I don't know, yeah, if there's a way you can change the mic just very quickly. Otherwise, it's very difficult to hear.
I'm wondering if you can just use the computer mic and audio, just remove the headset altogether.
Yeah, that might help.
Okay. Is it better now?
So far. Okay, carry on. Yeah.
Okay. Okay. So at last, I'm just using the clean data that they provide, the pre-processing data, which is the data that has already pre-processed and is clean data that I'm going to use to build the machine learning models. Okay. For the second one is the stimulus event analysis. The first one is event extractions. I first import the data, which is data that can provide from the data set, and also check for the events and event IDs, because this data set is actually included the imaginations and the perceptions informations. So for the events and events ID in the original data, it was actually a lot and looks like a mess. So I'm just like cleaning the event ID, which then eventually get the result of it. And also then the report annotations for each of the stimulus, which is across text, image, and audio. Okay. So this is the result for the ERP analysis across three different stimulus, which is the image, text, and audio. And we can see that there's actually a very different brain waves that we can see in each of different perceptions. And also I pick up one of the brain locations, which is in the midline parietals, and look up for the three different stimuli brain waves, and we can also see a very different signals in it. Okay, this is the topograph for three different stimulus, and we can also see that it's very obvious, which is all difference in three different stimulus, which is like in the image, there will be like more activations in the occipital parietal part, and also in audio is more activations in the temporal part. Okay, so for the machine learning classifications, the first step is doing the feature selections, which I use three different kinds of feature selections. The first one is PSD features, the second one is band power features, and the last one is time domain features. So this is the feature shapes for each of the feature selections, which I have 450 trials, which is 150 trials in each of the stimulus, and also the features that were selected in each of the different types of feature selections. Okay. Then I built three different feature sets, which is the first one is only including the feature selections of PSD, and the second one is PSD plus time domain, and the last one is PSD plus band power plus time domain. And I'm just going to compare the results of these three different feature sets. Okay, so the machine learning classification that I'm using is SVM, and this is the result for three different sets that I set in the previous step. Okay, so we can see that the results across these three different groups, we have the best test accuracy in the PSD plus time feature selections, and also, yeah, continued by the one that was PSD plus band plus time, and the last one is the feature selections that only contain PSD. Yeah. Although the accuracy was all looks quite okay, but yeah, the CV accuracy is only just above the probabilities a little bit. So maybe there could be better results that I can do in the future. Okay, so in conclusions, different stimuli like image, text, and audio actually evoke distinct brain wave patterns, which we can see that a lot of specialized regions of the brain process different types of informations. And overall machine learning performance are above chance, but maybe in the future we need more advanced features engineering or modelings to make better results. Yes, and for the future directions, maybe other people can expand the analysis to imagination-based tests because the dataset and originally they also included imagination part. So maybe in the future, people can expand analysis to imagination-based tests and also implement the deep learning approach. So that's all for my presentations today. Thank you.
You pass on to question time.
Yeah, hello. I have a few questions about your preprocessing. I just went through a code and you got like a runtime warning saying that estimated head radius is below the 3rd percentile for infant head size. Do you know what that is?
Oh, yeah, I don't really look at it. I forget which step I get that runtime error.
Yeah, like that's before you set the channel montage, I think. Yeah, I was just really interested in that. I've never seen that kind of warning before. And also, well, this is not like a bug, but it's kind of redundant. You referenced your data twice, once before the filter and later after the filter. Filtering doesn't undo the referencing, so you don't have to like redo the referencing. And before applying ICA, your high pass low frequency cutoff is 1 hertz, and later you use that bandpassed raw object for your downstream analysis. And a low frequency cutoff of 1 hertz is a little aggressive. So I was just wondering, like, you might want to kind of justify that, you know, that aggressive of a filter cutoff is appropriate. And yeah.
Okay.
Yeah, I was just going through a code, sorry, because you uploaded like just now. And also you performed ICA before your training and test split, which means that you actually have data leakage in your machine learning pipeline, meaning your model has actually seen information about the test set even before it got evaluated on the test set. So you might want to, you know, think about your artifact detection pipeline, because ICA in this pipeline, it will leak distributional information.
So is it means like I need to do ICA like after the machine learning models?
You could do it within each cross-validation fold, but that's really not feasible. So if you're like, you might, I'm not really sure about whether ICA really is appropriate in this pipeline, because it is an appropriate data cleaning method, but it kind of causes.
Sorry to cut you off. I think we're going a bit over time.
We'll
but
just kind of discuss this later. Yeah.
Yeah. Thank you very much. We're moving to the next person, Yu Ling, sorry. Yes, we see your screen.
Okay.
Yep. And we hear you loud and clear. Yep.
Okay. Hello, everyone. I am Weiyo Lin. I'm from Graduate Institute of Linguistics, NTU Taiwan. And the topic is the dynamic brain, how working memory capacity predicts attentional resource allocation and post-error cognitive adaptation. So this is investigating how individual differences in working memory capacity affect the way our brains allocate attention and cognitive resources under increasing mental workloads. So using event-related potentials, also EEG, especially the P300 component, I tracked the neural dynamics of 2 distinct groups. as they navigated through progressively challenging levels of an embedded task. And before diving into the data, so we can establish our theoretical framework. The P300 is a positive going deflection in the EEG waveform, peaking around 300 to 550 milliseconds post-stimulus, and primarily over parietal sites like PZ. When looking at the P300 wave, two things matter. One is amplitude, so tell us how many neural resources are being allocated to a task. And the next one is latency, so it tells us how fast the brain is processing the information. And so my project aims are, the first one is to identify the neural breaking point. So the threshold where working memory load exceeds cognitive capacity, and also compare how this differs between high and low working memory individuals. And the second one is to investigate the neurodynamics of the recovery versus the giving up phase after making errors. And next one is my pre-processing pipelines. Thank Amanda for giving me some very good suggestions. And to start my analysis, I imported the raw EEG files and standardized the channel names, because some names, the capitalized are different, to match the international 1020 system. Since there was no bad channels in the raw info, I built an automatic cleaning filter. So it automatically scans for hardware noise, dead channels, and extreme voltage spikes. And next one, I use the dual track filtering to clean the data without distorting ERP markers. So for an ICA track, I filter the data at 1 to 30 Hertz. And this aggressive filter removes slow drifts and makes it much easier to isolate eye blinks. And for the actual ERP analysis, I filtered from 0.1 to 30 Hertz to preserve the late latency components like P300. Then I slice the EEG into epochs spanning from 200 milliseconds before the stimulus to 800 milliseconds after. And I apply linear detrending to remove the DC offset. And next one, I use an extreme group design by taking the top 30% and bottom 30% group. I chose two backtasks as a grouping baseline because it avoids both ceiling and floor effects, and it offered highest statistical variance. So the middle 40% of participants were excluded to maximize the contrast between the high and low working memory groups. And instead of calculating the accuracy rate, a combined analysis of hit rate and false alarm rate provides evaluation of the strategies used under extreme cognitive overloads in the 4-back condition. And so the result is there are 6 people for each group. And the graph on the left is the hit rate, and the right one is the false alarm rate. So although the low working memory, the green line is the low working memory group, achieve a higher hit rate here, and rather than the high working memory group, but it was accompanied by the twofold false alarm rate. So which means they may keep pressing the button even when they are not so sure. And as you can see, the overall D prime values in low working memory group is negative. So in signal detection theory, a negative D prime indicates the participants had a significantly higher false alarm rate compared to their hit rate. So this captures the intense anxiety and uncertainty induced by the embedded task. So participants rely heavily on the risky guessing strategy, and they click the buttons impulsively. So, and the critical finding here is the high working memory group, the red line, consistently and outperform the low working group, the green line here, and at every single transition. So, which reveals that the high working memory group maintains a superior ability to distinguish signal from noise. So the low working memory groups in high performance was purely driven by random guessing, whereas the high memory group maintained the true executive control throughout the escalation of the cognitive load. And this is a breaking point of the behavioral data. So to truly understand our neural data, we have to look at the behavioral breaking point first. And this chart tracks the decrease in button press rate as the task gets harder, meaning a higher bar represents a more severe drop in performance or a strategy abandonment. So look at the high working memory in red. When moving from 1 back to 2 back, they show a sharp 14.2% drop. This is highly adaptive strategy. So their brains recognize the workload increase and they intentionally slow down to protect their accuracy. And because of this careful pacing, when they are pushed into the 2 to 3 back transition, they barely drop at all, only 2.3%. So they can maintain their control. But now look at the low memory group in green. They try to force their way through the early transition, dropping only 6.3%. But look at what happens when they hit the 2 to 3 back transition. The green bar rises to 8.7% and completely overtaking the high working memory group. So this is the exact behavioral realization of a neural breaking point we predicted. So their cognitive buffer is entirely overwhelmed, so leading to a severely strategic collapse. So by the time they reach 4 back, they hit the floor effect at minus 0.6%, and meaning that they had already disengaged during the previous stage. And move on to our neural evidence. So we can look at the P300 waveform here at PZ electrode. And our main area of focus is a shaded yellow block between 300 to 550 milliseconds post-stimulus, the standard window where the brain allocates attentional resources to process information. And look at the red line first, representing our high working memory group. So their P300 amplitude remains incredibly low, flat, and calm. But look at the green line, representing the low working memory group. It exhibits an explosive, hyperactivated spike that surges way past the grain average. So this is a clear demonstration of neural efficiency hypothesis in action. So a higher brainwave spike here does not mean better processing. So rather, it indicates severe cognitive strain. So the low working memory here are burning massive amounts of mental fuel and forcing compensatory efforts to stay afloat. So conversely, the high working memory individuals demonstrate a highly optimized, efficient neural pattern. Okay, and this is the grand average from 1 back to 4 back. Okay, so this is a very clear pattern. We can move from 1 back in blue and 2 back in orange and 3 back in green. It shows that the text gets tougher. The brain recruits more mental forces to handle the challenge. But the hardest level, that is a 4 back in red. Instead of climbing higher, the red line completely drop off and falls below the green line. So that means the working memory system maybe hit a ceiling, run out of gas, okay, and going to give up. And the next one, this one is the P300 cross 1 to 4 back in high working memory and low working memory. Okay, so look at the high working memory in red at 1 and 2 back. Their P300 amplitude is low and efficient. That means they don't struggle. But when they move to 3 and to 4 back, and the red wave begins to rise. So that shows them selectively unlocking their cognitive reserve and try to handle the heavy workload. But for the low working memory group in green, they are hyperactivated from the first and the second back. But when they reach the 4 back, they're exhausted and become a neural breakdown. So I'll quickly move to my second M. Okay, so this one talks about recovery or giving up phase. So this is the results, and also this is my favorite part in the in this data analysis. So I have to finish it. And the graph looks at the neural response and the immediate trial after an error, and maybe they will get a correct or wrong response. So, and we look at a blue and purple lines, that's a high working memory group. Okay, so whether they successfully recover in blue or make another mistake in purple, their brainwave remain very stable, positive, and control. Okay, and but the real drama happens in the low working memory group, the red line. If they manage to recover, their brain forces out high amplitude to stay in the game. But look at the green line, when represent a low capacity individual committing back-to-back errors, the wave completely craters, plunging deeply into a negative one. So this indicates a profound failure in post-error attentional recruitment. So this is a neural breakdown. Okay, and then I move to the conclusion. So, so I talk about the low-driven interaction and also the neural breaking point from low working memory and high working memory, and also analysis of the post-error in the last part. Okay, thank you.
Okay, thank you. I think in the interest of time, we will have to skip questions. So thanks. We'll move on to Yuting.
Okay, thank you.
I'm here.
Yeah, you share your screen. We can hear you.
Can you hear me? Okay, so I start my project, and this is the title of my project: building a Python-based FNIRS analysis pipeline with MNE Python. And my project started from a developmental FNIRS research question: whether lower grade and upper grade children share different MA-related brain activation. And for this final project, my main focus is method. I rebuilt the analysis workflow in MNE Python and compared it with an existing MATLAB nearest to a bus workflow. Okay, so the research question is whether lower grade and upper grade children differ in MA-related brain activation. And here I defined MA-related activation as the MA minus control contrast. So the group comparison is not simply raw MA activation. And between the two groups, so but the MA control contrast in upper grade children compared with the MA control contrast in lower grade children. And the local data set includes 131 children divided into grade 1 to grade 3 and grade 4 to 6. And before building the Python pipeline, I had used an existing MATLAB, which used nearest to a bus pipeline to obtain preliminary result for the NA-related good comparison. And this MATLAB result gave me a useful starting point. However, for this final project, I didn't want to only report the MATLAB result. I want to rebuild the workflow in Python and examine whether similar analysis steps in ME Python would produce comparable outputs. So why do I use Python and ME Python? It is because ME Python is designed for neurophysiological data analysis, and ME Python provides tools for FNIRS, preprocessing, and GLN analysis. And it was a good framework for this project. Okay, so let's move on to pipeline. And the pipeline starts from a local SNIRS files, and I load the data using NNE-Python, and then rename the original event maker into MA, PA, and the control, and check whether each participant has the required MA and the control events.
Sorry, can you define MAPA again?
Define MA, PA.
What is MA and PA? Sorry, I missed
PA,
that.
PA means morphological awareness.
Oh, okay.
Yes.
And MA is
morphological.
morpho and phono. Okay, got it.
Yes, and then I check whether each participant has the required MA and the control event. And for preprocessing, I resample the data, convert raw intensity to optical density, and then convert optical density to HBO and the HBR concentration. And after preprocessing, I run a first level GLN using NNE-Nears. And the model includes task regressor and the show separation regressor. And then I estimate the MA control contrast for each subject and use these contrast estimate for group level statistic and graphic visualization. And this is the Python result. I use the current NNE Python pipeline. I obtained preliminary group level result, and the analysis focused on long-distance HBO channel. And the results show no channel survived multiple comparison correction, and there were only a few uncorrected exploratory effects within each grade group, and no corrected group difference. So from the scientific side, the current Python results are exploratory, but from the method side, the pipeline successfully complete the full analysis workflow from S near F loading to group level statistics. And let's move on to another result. And this is the result from MATLAB. And in addition, the result produced by the MATLAB and the Python pipeline are also quite different. So this is the question I'm so interested. So can the MNE Python pipeline reproduce the MA, the nearest toolbox preprocessing outputs? My current answer is not exactly. And I started to think what caused the difference. So first step, I focused on preprocessing output validation because preprocessing is the earliest stage where MATLAB and only Python outputs can be directly compared. So I write validation scripts to find what caused the difference in preprocessing. And for preprocessing validation, I compare the output from MATLAB workflow and NNE Python workflow after preprocessing. And the first question was whether the time points were identical. And the current finding is that they were not fully aligned. And in the validation results, no subject had identical time grid lengths between the MATLAB and NNE outputs. And this means that the two pipelines didn't produce exactly the same time access after preprocessing. And the second question was whether the numerical values were identical. And the answer is no. No channels were exactly equal or uni-aware or close under the current comparison criteria. So at this stage, I cannot say that the NNE Python preprocessing output numerically reproduces the MATLAB output. And the third question was whether the signal shapes were similar. And here the answer is more nuanced. So signal shapes can still be similar, and the medial sample index correlation was high. And this suggests that the overall up and down patterns of signals may be similar in some cases. However, this is only a shape label diagnostics, and it doesn't mean that the two outputs are numerically equivalent. And the fourth question was whether the scale and our unit was consistent, and the correct answer is not yet. The Python 2 MATLAB standard deviation ratio showed a logical mismatch, suggesting that there may still be a unit or a scale difference between the two outputs. So overall, this finding suggests that similar pipeline states didn't produce numerically identical preprocessing output across the two platforms. Therefore, I interpret the current Python pipeline as an NLE-based implementation inspired by the MATLAB nearest to a bus workflow, but not as a strict one-to-one numerical representation. So in conclusion, the project rebuilt a developmental FNIRS analysis workflow in MLE Python and the MLE NIRS based on a research question about MA-related brain activation differences between lower and upper grade children. And the current Python results are exploratory and don't survive multiple compilation correction. More importantly, the MATLAB and NLE comparison show that the two pipelines are not strictly numerical equivalent. So in the preprocessing output validation, I found difference in time grid alignment, numerical values, and unit over scale. And for future work, I will further investigate the time grid alignment differences, unit and scale mismatch in the preprocessing default parameters, and then extend to validation to FRF modeling and the GLN software setting. And this is my presentation. Thank you.
Okay, thank you. Great work. So I want to check. I'm checking your GitHub. I only see MATLAB scripts. Did you put the Python scripts up there too?
Oh yes, I posted
You did.
too.
I don't see it there, but never mind. We can check it again. So I'm not able to see where the differences are. Yeah, but never mind. We can take that offline. But the other thing would be, is this normal that the MATLAB and the MNE don't match?
Not really normal for the EEG lab. Yeah, I actually wanted to ask, like, were you able to find out why the time points did not match? And since the time points did not match, it's actually, under that premise, it's actually quite normal that the values are not identical because the time points are not identical. So I was wondering, like, if it's related to resampling, because I actually saw her Python script, so she definitely had it up there. Because I saw in your script that you had like resampling and also like cropping, so that might be related to why the time points did not match. You might want to check the default parameters.
Yeah, I also thought maybe resampling may help clarify why things are different.
Yeah, so did you start from the very original file from FNIRS machine while using MNE Python?
Yes, I use MNE Python for data loading.
Okay, so I think one thing you can do is contact people from MNE and let them know what you know. Because I do that once several years ago while I try to import data I recorded from the MEG system as academic SNICA, because so at that time I cannot do that. So I asked them for their help, and then they asked me to whether I can access the source file that the machine generated the recorded file, and then I contacted the Japanese engineer, asked them whether can they share that, and then they do give that source file to me because we have a very good connection. So then I passed the file to MNE people, then they solve the problem for me. Yeah. So So yeah, you can try to ask their suggestions, and they may tell you, well, they need either more information from the provider of the machine, or some more detail in regarding how the file is created. Yeah, usually it will help you to solve the problem. Yeah. Okay.
We spend more time on this because this is important, right? You have tools from M&E and MATLAB, and I think that would be a great thing. So if you're spending this time, it will be worth it. Yeah.
Yeah, and I just add a little more information. So I tried. So from my previous experience, I try to like make sure every number I saw in the MEG machine are the same as I found after importing the data into ME, and after they make an update, everything looks the same to me. So then yeah, so you can try to work on that way.
Okay, thank you.
And I like categorically, yeah, I see your Python code now. It's because you have two repos, you don't, not just one, right? Okay, so got it. Thanks.
Thank you, everyone. We move on to Ziwing and Marcus.
Hi, morning, afternoon. Can you see my slides?
Yes.
Okay, hi. Good afternoon. I'm Marcus, and today I'm presenting on our project about a multidimensional approach to examining aggression vulnerability with looking at psychosocial factors and structural variations in the amygdala and the prefrontal cortex. Just quick background, we chose aggression because Wing and I both have experience working in the prison, and so aggressive behaviors is something that's interesting to us, and also relates to day-to-day life, why some people can be more aggressive than others. So what we decided to look at is the continuous psychometric variables and those that have neural associations. So doing some literature review, we recognize that though there have been a lot of research studies done already on aggression, they tend to mainly be self-report measures or behavioral paradigms. So they are often in silos or done separately from biological or neural explanations. So we thought it would be a good way to understand it more holistically as well. And also because reactive aggression tends to be not understood by these two measures. Then looking at neuroimaging research, we recognize that the two main regions of interest tends to be the amygdala and the prefrontal cortex, because the amygdala is meant to be more of the emotional processing systems, and the prefrontal cortex is meant to be more of the executive control systems. But again, these studies are done apart from these self-report behavioral measures. So that was our original idea, was then to see if there was any functional connectivity between the two regions of PFC and amygdala, and how they relate to the psychosocial factors. Unfortunately, because we were both unable to access the Human Connectome project, the resting state or the pre-processed data, we had to pivot. And so we instead moved from functional connectivity to the structural variations. Yeah, so is there a background for the structural variations as well? Yes, the smaller amygdala volumes tend to have high levels of aggression and violence. Also, interestingly, while this is the case for most general healthy populations, in some affective psychosis and bipolar disorder, the relationship tends to be reversed, where an increased volume of amygdala is also associated with higher aggressive behaviors, but that tends to be more because of the disorder than just the volume of the amygdala in itself. Then for the PFC side, the prefrontal cortex side, we recognize that lower prefrontal cortex tends to be related with antisocial personality disorder. While there's no direct research on PFC and aggression, we do know that increased antisocial personality disorder tends to have high levels of aggression. So there's no direct link, and that kind of brings us also to our study. So we recognize that there's a lack of understanding between these biological factors and psychosocial factors. So we want to see, is there a relationship, and can this relationship tell us if these people are more predisposed to vulnerabilities to aggressive behaviors? So looking at our literature review, we look at 5 main psychosocial factors. Again, just for simplicity, that every factor here will increase aggression. So increase in stress, decrease in self-efficacy, decrease in support, increase in conflict, increase in rejection, and decrease in inhibition, as well as in personality, decrease in agreeableness and conscientiousness in the literature tends to increase aggression. So then our research question becomes, do any of these aggression-related psychosocial factors that I previously mentioned associate with any structural variations in the amygdala and the prefrontal cortex? And also furthermore, because of the data that we have, we could only have age and gender. So we're also curious to see can this be moderated by age and gender? So also based on the feedback that we got previously that we had too many hypotheses, we reduced it down to two main ones. The first being, is there a main association between any of the psychosocial factors as well as related to structural variations in the amygdala and prefrontal cortex? And the two main regions that we use for the prefrontal cortex will be the medial orbital frontal cortex and the rostral anterior cingulate cortex. And then for the other part, the other hypothesis is, can these relationships within the amygdala PFC structural balance, is there any is it moderated by age and gender? Yeah, so for methods, the data set that we use is we still use the human connectome project, but just couldn't access the pre-processed data and the resting state fMRI. The age range was around 22 to 35 years old, and they were collected from the range of around 2012 to 2015. So these are the exact variables that we use from the data set. The demographic data are just gender and age range. The psychosocial factors, the ones that we listed that we were interested in finding, are related to each of the individual variables. And then originally we had 9 brain structures, but you notice that some of them are for the left and the right side of the brain. So what we decided to do is we combine them from 9 brain structures into 4. Oops, sorry, I moved to change slide, but we moved it from 9 brain structures to 4 main brain measures. And then the reason why we decided to do this was because this was meant to just simplify our project, as well as because the left and right sides aggression in general tends to be bilateral. And so in the left and right volumes also tend to be highly correlated. So just at the bottom here, these 4 are just the ways that we used it. I'll combine them. Okay, so what was our methods? We use the structural MRI for new imaging data, and then we focus on the prefrontal cortex and the amygdala. Then how did we clean the data? So what we did was first we had two main sections. The first was the data cleaning and then the analysis. So typical data cleaning, we merge and clean the data because they were from 2 different data sets. Then we check for any outliers. For the analysis side, we did bivariate person correlations. Because there were so many different pairs, we also had to do FDR correction. Then after that, we also did OLS moderation regression, and we visualized that interaction effect. Okay, so they consist of 2 different data sets. We combined them, and then that dropped all the missing cases, which led from 1,200 participants to around 1,105 participants. And then we screened that 4 brain region of interest measures that we mentioned earlier. And then we did a Z-score to remove any extreme outliers. So anything that was more than 4 standard deviations apart were removed. As long as they had one of the brain measures that had missing data or was outlier, then we removed the entire row. So even though the total number of outliers we found here is 20, we in the end only removed 17 because some of the rows had multiple outliers. Yeah, so in the end, after that, we had a final analytic sample of 1,088 participants. Okay, so what kind of analysis did we do? We did bivariate correlations between the brain structures and as all the psychosocial measures that we had. And actually, the findings was that they were all very weak, and that around R is less than or equals to 0.08. Even after, expected, but even after we did the FDR, we found that there was actually 0 pairs that were significant. So that means our findings is there's actually like no association. And this finding shows that it only explains about 1% of variance. So so our findings is that there was no association. So after which we did the FDR correction because there are so many multi-comparisons. So what we decided to do next is that we also did a composite and moderation analysis. So we aggregated all the reason we did this is because while there are no individual effects, maybe there might be systems level effects that we might have missed. So we did first of all, we composite all the aggressive factors that we had, like anger effect, anger hostility, anger aggression, passive hostility, and as well as the amygdala PFC balance. So this just means that how big is the amygdala relative to the prefrontal cortex. So higher means there's a larger amygdala in general. Oh, sorry, duplicate slides. Yes. Ooh. So based on our analysis, we recognize that actually by itself, the PFC balance doesn't really have any effect, but actually gender does, which I would say is not very surprising, but yes, so males tend to have higher aggressive behaviors than females. when we put them together, there was no interaction effect. It was not significant. With regards to age, it tends to be there was higher aggression the younger the participants are, and this was the only interaction effect that we had, is that actually, while it's true that older participants are less aggressive, older participants with larger amygdala relative to their prefrontal cortex tends to have more aggressive behaviors than their counterparts without. Yeah, so this was the overall model that we used. Yes. Yeah, and it says, like I said, that the interaction is significant, but the brain behavior relationship depends on age. Okay, so what were our key findings? Is that unfortunately or fortunately, the brain behavior associations were null, and none of them actually survive FDR correction. So good to know, I guess. Then also the second finding is that composite amygdala PFC balance interacts with age. Which means that I mentioned earlier that there is some sort of link between regional brain structures and aggression, and they might shift across time rather than being a fixed effect across ages. Yeah, and lastly is that key findings is that structure alone may not be sufficient to explain why there's variations, and that maybe there are other moderators like age and gender that could explain more for the differences. In the future directions, I think we will hope that we can actually use the functional connectivity and the functional neural processes, and not just the structure, but because of the time constraint, that was what we did. And also, maybe we could model age as a moderator rather than just a covariate. And we want to see also if whether the balance of age effect that we found can be replicated across samples with a wider age range. Yeah, thank you.
Okay, thanks. I'm wondering if you could try maybe not just targeting the amygdala or those regions. Are you able to do like a whole brain regional kind of, composite, just like what you had from the aggression? You had different aggression scores, and then you tried to find a composite. Perhaps you could find a composite across the whole brain, and then kind of use that approach to find their kind of patterns in the whole brain structure that jointly bear on the pattern of aggression.
I think moving forward, that will be a good idea. The main reason we just chose these two is because the literature tends to say that these two regions are what's related, but I think it'll be good also if we can do more regions.
Yeah. I mean, if you're limited to only this data, then that is the best, kind of thing you can do moving forward. But of course, it'd be better if you could get raw data and have a bit more real brain stuff, like the detail, so to speak. But yeah, okay, bring it up, thanks.
Yeah, one related question. Sorry, somebody else wanted to ask a question. Yeah, good job trying to look at this, that you did 1,000 over subjects analysis. What is your formula for your balance?
Sorry, what is that?
You had a balance index, right? You calculated something about balance there?
Yeah.
What formula did you use? Because it's like you had two regions, right?
Yeah, I did. Are you able to still see my screen?
Yeah.
Yeah, just the volume minus the average of the gray matter volumes of the PFC.
But what's the balance thing? Didn't you want to look at? Are you looking at amygdala and PFC balance, or
yeah? So we want to see if
that.
Also, we just want to see if the amygdala is larger on average than the PFC.
So you're using the Z of the amygdala, or are you using like a normalized for both? Because all regions are not the same size, right? So you are doing Z as in the distribution, or you're normalizing it?
So this is pre-norm. So we just want to see relative, what is the differences, like because we understand there's variations in size. So we want to see across, like, how big is that variation?
Yeah. So usually variation in size, yeah. But because the both volumes are different, you may want to normalize it within each ROI, and then do your regular, the amygdala minus, one direction, amygdala minus PFC over amygdala plus PFC, right? For the regular sort of like an asymmetry, but it's sort of like a balance index. Then that will give you a more, of course, there are many arguments about different kinds of balance index, but do the bare minimum. So at least you know it's sort of normalized and equated.
Okay.
Yeah.
I think most probably we can normalize it.
Actually, I would propose a proportion or something.
Yeah.
What? Sorry.
Like percentage of the brain of both
okay.
regions, or some ratio rather than a subtraction, something like that.
Okay.
Yeah. So that one would become a ratio. So it's like, so it's like when you look at asymmetry index, it's very similar to that. So you could, yeah, look at that literature.
Okay, thank you so much. I'll look at it.
Marcus, if I heard correctly, you pull together the right and the left hemisphere together for this arrow,
Yes.
right? And I'm not familiar with this literature, but I wonder if there are, because it's more emotional related, I wonder if there will be like hemispheric symmetry. And when you put together both sides, maybe that would attenuate the variations.
Okay, unfortunately, I didn't get the chance to see if we use them as individual variables, but the reason we did that was because there were already so many comparisons. So if really with the correction, it was really, the likelihood of getting a single character is really quite low. So that's why we reduced them. And also because, like I mentioned earlier, we found that there's actually, regression tends to be more bilateral, so it's not really related to one section. But I guess if in future time, we could also try to see if the different regions will be effective as well, or that maybe one side, the left side, right side might have more impact on aggression. Yeah.
Thank you.
Thank you.
Thank you very much. Now moving on to the next person, we'll move on to Xingqi. Yep.
Can you see my screen?
Yes, we could.
I am Xinqi. I'm a first-year psychology master student in psychology, and this is my final project topic: a replication study about which region of the brain has significant activation during social cognition tasks. I used the open neural dataset. It is a multi-echo fMRI data, and in the original paper, it said they use theory of mind tasks to define the functional RIs for social reasoning. In my analysis, I used pair t-test, and I set the contrast to be belief trial greater than photo trial, which means the clusters will be the region that have significantly greater activation in the belief trial compared to the photo trial. And there are totally 7 clusters that survive my correction. So in today's presentation, I will talk about the difference between my result and the authors, and the pre-processing I've used, and the problems I've ran into, and how did I solve them, and the open science operation I've done. So first of all, these are the 7 clusters in my results. And among them, there are 4 are the same as the authors. What about the 3 remaining? I think they are not specific to the theory of mind task, and they are more like visual processing regions. Maybe because the stimuli was more complex in the theory of mind, the belief trial. So what are the temporal pole and medial prefrontal cortex, which are not in my results? I came up with 3 possible causes. The first is that actually the author's results is 1 representative participant, and mine is from 10 subjects from group analysis. And the second is actually I've set a wrong parameter in my smoothing steps. I then change it from 5 to 7, but I think there's probably still something wrong. I have to check my script. And the third one is actually the author used a lot of denoising step because it is a multi-echo fMRI data. But I'm still thinking did I need more denoising, or what else can I do? And that connect to my next part, which is how do I preprocess my fMRI data? This is the comparison of my preprocessing and the authors. This shows that the steps that might share the same purpose and concepts, and these are the steps that I didn't use, and these are from the author's steps. And what are the purpose and concepts? Spiking means to remove transient signal spikes, and single-shot transformation means avoiding image blurring caused by multiple interpolation steps. And multi-echo ICA means retaining both related components while removing non-both noise components. As for optimal combination, is that it is multi-echo images were optimally combined using echo-specific weights to maximize both contrast and signal-to-noise ratio. And global signal regression means removing global brain-wide signal fluctuation. Motion sensory means removing time points with excessive head motion. I was thinking, are the difference caused by these denoising steps? I think there's a lot for me to learn, so I also want to hear about your thoughts. So when it comes to my learning, I will talk about what are the problems I ran into during the process and how did I solve them. There are 3 of them, and they are all from the pre-processing progress. The first is which runs T1 and T2 image should I use? Actually, there are totally 3 runs, and then after quality checking, I select the run 2. And the second is when I do Dartle create SST, it failed because MATLAB can't open file for writing. So I copy all the subjects RC files from the Linux system to my Windows system. And the last one is that the Dartle normalization MNI, when I do this step, I found that the voxel size is not a traditional one. Then I called for help in the community, and I found that I have to use this parameter of 7 to do the Gaussian for width and have maximum. So this is my conclusion. I think quality checking is needed, and file and software are better in the same system. Informal training and community matters. When it comes to community, I think open science matter. So I have done some practice. I have done some operation to the open science, and this is my repo. You can see this is the file structure of my repo. There are totally 4 folders in my repo. And in a repo, you can see how do I get the data, how do I do pre-processing, how do I do subject level analysis and group level analysis, and I figure the results. I think SPN can function using the .m script. And you can see there are 2 kinds of scripts, which is .m and the other is job.m. They should be run at the same time. The left one is .m, and it should be run with the job.m script. And be carefully. And I just found that there are totally over 7,000 lines of scripts in the job.m file. And if you need to know what parameters or derivatives from the steps, I take some notes and also push to my repo. And other information can also be found in the document folder. And feedbacks are welcome. After you do the analysis, you can see are your results the same as mine? So in sum, this is my the result of my replication study. So for my next step, I was thinking if I'm going to learn how to do outline analysis and to see if the temporal pole and medial prefrontal cortex will survive correction and get the output figure like this at the right. This project is especially thanks to Josh tutorials and imaging centers, and those who answer my question, teachers, TAs, BH community, my friends and labs. And thanks for listening.
Hey, thanks. So the authors figured that one. Can you tell me which figure? Because I'm looking at the paper. Is it like their figure 2? It doesn't look exactly the same.
You want to know what are the regions?
No, I want to see, because so that one is, I think they show one representative subject.
Yes, yes, yes.
But yours is the average of 10 subject.
Yeah.
Yeah, that really makes it difficult because you don't know which subject they use.
Yeah, I don't know.
So you cannot like find the same subject and see if you exactly replicate. Yeah.
So how do I?
Well,
I think the medial prefrontal cortex and temporal
yeah.
are.
I mean, yeah, I think we can find some commonalities, but I think what we're more worried first at the first step is the technical part. Whether anything that we are doing, you know, numerically is different from what they are doing, rather than, you know, we assume that we are roughly doing the same thing and then we can roughly interpret the result. It may be that there's something just wrong with our step, or we are not doing it right. As you say, the pre-processing step is quite different because they are incorporating the multi-echo thing, which generally we don't. Yeah, so maybe that would be important. I mean, I'm trying to avoid it, but it sounds like if you want to pursue this, it is worthwhile to write to the authors and then ask them, hey, which subject is it? And then can I, you know, as in your goal here is you want to create the same picture exactly. Then you know that you've got your steps right, you see? And then from there, you can move on to more advanced stuff. You know, kind of like you solve this problem. Yeah. So right now it's still inconclusive. It makes sense, but then it doesn't feel very, you know, right, confident yet, right?
It seems I have to send an email to the author and ask.
If you really want to, if this is something that interests you and you want to, then yes, it will be a worthwhile thing down the road.
But actually, I just want to do how to
do the analysis. Well, then the suggestion would be then maybe you can find another data set that would be easier to replicate.
Okay.
As opposed to this one. Yeah. Yeah. Okay.
Okay, thank you. We'll just move on to the next group. It's Patrick, Lin, and Yuling. Yeah.
Hello.
Your screen. Yeah.
Okay. Hello, everyone. I'm Lin Yichen, and my partner is Yu Ling, and we're from NTU-TW Department of Psychology. And our project is about examining affordance and motor representation in the dorsal visual pathway and motor-related areas. Okay. So let's start from a quick recap of our research topic. We're interested in how affordance represented in our brain. According to Gibson's definition, affordance are the properties that environments or objects offer to humans or animals, and the properties may be different due to the ability, intentions, and goals of the subjects. And affordance serves as an interface to influence our perception and actions. So, for example, I believe most of us will use spoon like the left-hand side rather like the left-hand side and right-hand side. And many previous studies have suggested that several dorsal string regions are involved in affordance processing. For example, AIP, IPL, and macaques, also macaques V6A, have been linked to affordance-related functions. These regions are considered potential neural correlates of affordance because they are involved in representation object use knowledge, processing affordance information, and transforming visual information in motor regions. So the goal of our project is to use things that have fMRI dataset to explore the neural correlates of affordance. Things is a large-scale multimodal dataset development to study visual and semantic object representations. It includes several behavioral measurements and a lot of neural recording, like probability ratings or fMRI, MEG, and also macaque's neural activity recording. The dataset contains more than 1,800 object concepts and over 26,000 natural realities object images. And we use Things fMRI data. Things fMRI data provides processed single images, meaning that we can obtain a neural activation pattern for each image. The stimuli include 720 object concepts with 12 different images for each concept, presented in a randomized order during the experiment. Using the condition files accompanied with each run, we can identify the trials corresponding to each object and extract the object's neural responses individually. And this allows us to estimate the neural representations for each object and each image. So to explore the neural correlates of affordance, the first hypothesis of our research is whether objects with similar affordance may evoke similar neural representations in motor and affordance-related areas. To test this hypothesis, we select object concepts that share similar affordance as well as concepts with different affordance. Then we can construct some representational dissimilarity metrics in our ROI. If affordance information is represented in these areas, we can expect that objects with similar affordance may show some similar neural representations. And the second hypothesis is we expected that motor and affordance-related regions may share similar representational structures. To test this, we perform representational similarity analysis between regions of interest. If these regions encode similar affordance-related information, these brain regions may have similar representation dissimilarity metrics. In contrast, if these brain regions encode different information, the correlation between these RDM may be relatively low.
Okay, so now let's move on to our results. In our initial attempt, we subjectively select 8 object concepts and categorize them into 4 action-related pairs, such as calculator and typewriter, or tongues and tweeters. We expected to see distinct clustering pattern in the audience of motor-related areas, specifically AIP, IPL, and VPM. However, as shown here, the initial results did not reveal any clear or expected patterns. This suggested that strict subjective categorization might not capture the complex underlying neural representation under the conditions of our project. So to overcome this limitation, we shift our methodological strategy in the second phase. Instead of relying on subjective grouping, we adopted a more data-driven approach. We expand our selection to 35 comprehensive tool concepts chosen from the 720 categories in the Things Plus dataset. Based on these 35 concepts, we reconstructed the brain audience and performed a RSA to systematically examine the representational connectivity both within the dorsal stream and between the dorsal and ventral streams. In the beginning, we tried lateral occipital complex and PIT cortex and VVC as the ventral stream. but both LO and PIT are not available in the dataset. So we have only chosen VVC to analyze. And this slide display our cross-region RSA results, and notably all statistical tests here are significant. Let's look at the top row first, which reflects the relationship within the dorsal stream, and the RDMs of AIP and IPO are highly correlated, showing that these parietal areas are deeply synchronized during tour viewing. Meanwhile, the ventral premotor cortex also shows a significant and positive correlation with both AIP and IPL. In contrast, the bottom row demonstrates that the correlations between all dorsal areas and contrast confirms our second hypothesis. In conclusion, although we initially couldn't find the expected item level clustering in motor-related RDMs, which might be due to uncontrolled low-level visual features in natural images, our RSA still provides some insights. We demonstrated clear representational correlations within the affordance-related areas and low to zero correlations between these dorsal regions and ventral tour-related areas. Therefore, we infer that dorsal pathway primarily represents object motor and affordance information, rather than the object's semantic category, which is processed by the ventral stream. Finally, for our future directions, we have two concrete plans. First, we realize the naturalistic images in the THINS dataset contain a lot of noise. We want to ensure our analysis pipeline is full reliable. To do this, we would and we should run a benchmark control test using the classic VES versus SIN contrast in the FFA and PPA. If this robust effect replicates, it proves that our code and dataset are working good. And secondly, in addition to our current RSA analysis, which looks at the continuous geometry of the brain space, we plan to apply linear SVM decoding. Since fMR data is highly noisy, SVM can maybe automatically atomize voxel weights. This may allow us to see more precisely whether motor areas like AIP and IPO can successfully classify different tool categories. So that's all our presentation today. Thank you.
Thanks. So can I clarify again? So you didn't find the item level similarity RSA, right? But you found yeah.
Yes, we didn't find concept levels.
You didn't find concept levels, but you found affordance level.
Affordance level.
Right? The next one where you found that was which level?
This is
no, the one where you had the 0.5 correlation that you had in the parietal. That one is what?
This one is also concept level. This means that.
Oh, but then so you have that, yeah.
This means that in AIP and IPLs that we both construct these concept levels RDM, and the representation between these two regions are significant.
Oh, so those are like between regions similarities.
Between regions, right? So these six are all between region similarity, and the upper row is within motor-related regions, and the bottom row is compare ventral pathway and dorsal pathway. And the ventral pathway regions we select VVC, which is previous study suggests that VVC can present tool use, present tools, represent tools.
Okay, and can I just confirm that when you say, let's say you got inferior parietal lobe region, that what you did was you extracted all the voxels there, the responses, right?
Yes, we
all
extract all the inferior parietal lobe voxels.
all the voxels, and then you match the pattern of the voxels in one condition or one trial to another. That's right. Is that right?
We average every trials in the same concepts. And
average trial. Okay. Now I'm just trying to find out why you didn't find it. Could it be because of that you are doing some sort of averaging when actually you could do trial by trial sort of?
We have to do trial by trial.
And
yes, but the pattern still didn't show any expected patterns across concept or within, even within concept, we can see the patterns.
Sure. Okay. Well, sometimes that's just the data. All right. Thanks.
Okay.
Now we'll just move on to the last person for the day. That would be Chelsea.
Hi.
Yeah, can you share screen? We hear you loud and clear.
Yes, oh, sorry.
Okay, can you guys see?
Yep.
All right. So, oh my God, it's lagging. Okay, sorry for the switching to the last in the beginning. I'm so sorry because of the power outage at my house here, and it did cut off the internet. That's why I kind of panicked. If it's just like, if the lights are just down.
Your 10 minutes is cut from here.
Yeah. Okay. Hi everyone. I'm Struan, and you can call me Chelsea, and I'm a first year graduate student here at the GIBMS, and today I'll present my the main idea is simple. Before we do deeper neuroimaging analysis, we need to make sure that the data structure is actually inspectable and trustworthy. And for task fMRI, this means more than just having brain images. We also need to have event files and behavioral and stimulus metadata, configuration rules, a QC script, and finally a report that can show summaries and warnings. So this project focuses on a lightweight workflow that links event metadata with imaging file structure and produces QC reports, readable QC reports before further analysis begins. So the motivation started from a task fMRI setting where each trial generates multiple layers of information. And so in this example, a participant first sees a fixation, then listens to a probe melody and makes a yes or no decision, sees another fixation, and then hears an outcome melody. And from this kind of task, we do not only get brain images, we also get metadata, subject run, trial number, onset, duration, stimulus features, decision, reaction time, and outcome information. After the pitch, 2 weeks data to be useful which bold file belongs to this run? Does every event file have a matching bold image? Are there bold images without matching event files? And can the report flag these mismatches clearly? So that's why I would describe my project now as data readiness, QC, rather than just only trial-wise. So, okay. Obviously, task fMRI data can be hard to organize and understand. In a real data set, there may be source data, behavioral logs, stimulus information, and original scanner files. And there's raw data with anatomical and functional imaging files for each subject. There also may be derivatives, pre-processing outputs, reports, and QC files. So, I turned this pain point into a reproducible data readiness workflow. The quiet errors can be costly here, since some problems are event metadata problems. Other problems are imaging file problems. For example, bold or T1 weighted files might be missing. Image file extensions might not match our assumptions, or sidecar files may be missing. Yeah, one actual issue I encountered was assuming all bold files would be the NI gzips. When one Open Neuro dataset actually used nifty files instead, and there also might be cross-layer problems. An event file might exist without a matching bold file, or a bold file might exist without matching events. Also, subject and run labels can also fail to match, and these problems may not immediately crash a pipeline, but they can distort the downstream analysis and make datasets hard to reuse and waste time if they're discovered too late. So the core design is configurable rather than dataset specific, and input data can include events TSV files and an imaging file listing, and then config file defines which columns matter and what file patterns to expect. And then the whole workflow validates, summarizes, and matches the files, and then it outputs tables and warnings. Yeah, okay. So for example, one dataset may use genre and track as important event columns here, and another dataset might use trial type, response and reaction time, etc. And if the script hardcodes one experiment and then becomes much less reusable, so the config file acts like a bridge between the general quality control logic and the specific dataset. And the same workflow can adapt to both music and non-music task fMRI datasets by changing the config expectations rather than rewriting the whole script. So yeah, all right, let's move to the implemented prototype. For implementation, a working prototype was built. It performs remote Open Neuro file inventory smoke tests. The script takes an Open Neuro S3 listing, a report output path, and a dataset label, and it detects bold files, event TSV files, T1 weighted anatomical files, and JSON sidecars. And it also cross-checks event files and bold files by normalizing the file name base and checking whether each event file has a corresponding bold file. In addition to the file inventory, I also downloaded and inspected selected lightweight event TSV examples. So the workflow does not only count files, it also begins to inspect real event table content. And the output is a markdown QC report. And yeah, so to test the workflow, I ran 2 Open Neuro smoke tests. So the first data set was DS003720, a music fMRI data set. The workflow detected 5 subjects, 90 bold nifty files, 90 event TSV files, and 5 T1 weighted anatomical files. And yeah, so there were 0 event bold mismatches. And the second data set was DS7, a non-music stop signal task data set. So this detected 20 subjects, 118 bold files, 118 events TSV files, and 20 T1 weighted anatomical files. And again, the mismatch count was 0. So it's not, the point is not that these data sets are fully validated or scientifically analyzed, but the point is that the same quality control logic could be applied to both music fMRI dataset and non-music fMRI dataset. So, all right, the next part is even if the file matching works, do the event tables look the same? Well, no, and that is exactly why configurability matters. And so for the music fMRI dataset, I checked 1 events file with 41 rows. The required timing columns, onset and duration were present, and the meaningful task-specific columns included genre, track, start, and end. And for the non-music dataset, the stop signal dataset, I checked 1 events file with 128 rows. It also had onset and duration, but the meaningful task-specific columns were different. So it's trial type, response, reaction time, correct, go, and the suck stop, which stands for successful stop. So the shared bid style structure gives us a common starting point, but the experiment specific columns would vary. And yeah, that's why workflow should be configurable. The logic can stay similar, while the config tells it what columns matter for each data set. And so, okay, this slide summarizes what the prototype actually produced. First, there's code and configuration, the main QC script, plus the config examples for both data sets, and the file patterns include both the nifties and the NI gzips, which came directly from debugging the first Open Neural Smoke test. And there's a demo or sample data, and I did not store full imaging data in the repository. I stored only small event TSV examples, which are safe and lightweight for a public repo. And then there are also generated QC reports, Open Neural Smoke test reports, event table content checks, and an open data comparison report. So yeah, together these support a reproducible quality control story before deeper analysis. And okay, the script, finally, the script detects bold files by checking for both nifty NI gypsies and nifty extensions. It detects event files, strips the file name suffixes to normalize the base names, and then compares event bases with bold bases. And if there are event files without bold files or bold files without event files, the report can flag those as a warning. So yeah, current prototype checks remote Open Neural file inventory, bold and event file counts, T1 weighted and sidecar counts, event bold matching across runs, and markdown reports with warnings. So yeah, next step is to make the script read the YAML configs directly and add NI Babel-based nifty readability checks, validate image, shape, header information, and maybe bold volume counts, and add unit tests. Thank you.
Okay, thanks, Chelsea. This is great work, and you validated it on 2 Open Neural data sets. Is that right?
Yeah.
2 different ones. I guess I'm wondering if this is just an advice as NS also moving forward, if you could generate a, I don't know, maybe a more intuitive graphic of the checks or the stages of this pipeline, at which stage. I'm thinking something visual, like I have the data on the left side, and then I have outputs on the right side, and then in between it's a timeline, and then in between is like, what steps are what's done and what are the intermediate outputs, something like that, so that a user, when just looking at your repo, would be more immediately grasp graphically, what this tool does. So you could think about something like that.
Okay.
Okay, and then, sort of a more explicit instruction or description about usage, because this is a useful tool. However, if people do not understand how to use it, then it is not a useful tool, right?
That's true.
So think about that and try to make the repo a little bit more engaging, user-friendly, and just, very informative. Yeah.
Okay. Thanks,
Okay.
Josh.
As for me, I don't know if other people have questions for Chelsea about that.
It's great job for reproducibility.
Thank you, Professor Annabelle.
Yeah, first step in all reproducibility.
That's also kind of a learning. This is an opportunity for learning. Like throughout my first. Actually, this is my first semester here at Josh's lab. So I take this also as an opportunity to familiarize myself with organizing fMRI data.
Yeah, very nice. Okay, thanks. Is that it? That was the last person. Okay, great. Congratulations to everyone to present today. You're done for the semester. And hopefully we will see you, most of you, if not all of you, in Singapore. And in Singapore, I just want to say, I think, Annabelle, I'm not sure, or the other professors, feel this, but I think like we can definitely feel people have moved forward from their pitch quite visibly, quite obviously. And I think this is a great indication. And I'm actually looking forward to, for those of you going to Singapore, to present an even more refined version. So, you know, great job, everyone. I'm really excited. And I see all your project pitches also, all your repos on the GitHub. And I think it's just very awesome. So yeah, great job, everyone. I hope that when you go to Singapore, you can use the opportunity to interact with the Singapore side, the team more, so that there's more crosstalk. And maybe through that, even more amazing things can happen in your projects, or you might even come up with new projects to do during your time there. So that's just something to share with everyone. Yeah.
Yeah,
Okay.
I echo what Joshua just mentioned, but also I guess the news is your work is actually not done because you're still trying to summarize and put it up on the BrainHack website. And I hope that the Singapore Symposium is an opportunity for you to sort of completely pitch your completed project on the website to get people to go there and take a look and vote for you. So we look forward to that.
There's a competition. Is that? Oh, wow. Okay. What do they win?
We haven't
Free
decided.
chicken rice. Free plate
I
of
think
chicken.
the prize is not so much of the attraction. It's
Yeah.
more of people really go in and read your hard work.
Yeah.